Okay, so the binomial distributions are important in statistics when we want to make inferences about the proportion of proportion P of successes in a population. So suppose we had 10% of CDs that have defective copy protection schemes that can harm computers. A music distributor inspects an SRS of 10 CDs from a shipment of 10,000. Let the random variable x equal the number of defective CDs. What is the probability that a shipment will have no defective CDs? Okay, so first off, it's not quite a binomial setting. So if you remove one CD from the shipment, the proportion of bad CDs remaining in the shipment is different, right? So the conditional probability that the second CD chosen is bad, when we know that the first one is good or bad, it changes the probability for the remaining CDs in that shipment. Okay, so the distribution of X is very close to the binomial distribution with n equals 10, and your probability here is 0.1, yes, 10%, okay? But it isn't quite a binomial setting. So in other words, what we're looking at is it's not a binomial setting, but because it's very close to it, we're going to use a binomial setting anyways. So the next thing is going to show you actually why it is that we can do this. So the actual probability of it being no defects would be 9,000 over 10,000, that's what the shipment starts with. If you pull out a bad one, then it goes down to 8,999, and so on, till you take out those 10, that SRS of 10 CDs. Okay. If you were to use a binomial distribution with with x equaling 0, I have 10 trials. I'm looking for no defects or no bad CDs, okay? The probability of a success would be 0.10. That's the 10% are defective. We want 0 of those. Times of fail would be 0.9 times 10 of those. I get a number that is not the same, but it is very, very close. So in practice, almost all so in practice, these probabilities are so close together. So despite the fact that it's not exactly a binomial setting, because it's not necessarily independent, what happens on the first will affect the next. It violates that I in bins. We're still going to do it because of a certain situation. So almost all real-world sampling, such as taking an SRS from a population of interest, is done without replacement. So that's violating that independence condition when you take something out and you don't put it back. So if you take out a bad CD, it's a different amount in the shipment now. So the CD example shows how we can use a binomial distribution in the statistical setting of selecting an SRS. When the population is much larger than the sample, a count of successes in an SRS of size n is going to be approximately binomial distribution. So your entire shipment here had 10,000. We were just taking a very small sample, just 10. So even though it's not independent because we're taking out and not putting back in, we're not replacing. The fact that the entire population was 10,000 and we were only taking 10 because it was such a small sample, we can still use a binomial setting. So when counts as much larger, so in practice, the binomial distribution gives a good approximation as long as we don't sample more than 10% of the population. So as long as we're under 10% of your entire population, so 10 is definitely less than 10% of 10,000, you can go ahead and use a binomial a binomial distribution or binomial probabilities for these problems. So that's going to be known as your 10% condition. So when taking the SRS of size n from a population of size n, we can use a binomial distribution to model the count of successes as long as your sample is 1/10 of your population, or less than or equal to 1/10 of your population. Okay, so this is just a quick example to show this. Okay, so example, hiring discrimination, it just won't fly. So sampling without replacement. An airline just finished training 25 first officers, 15 male and 10 female, to become captains. Unfortunately, only 8 captain positions are available right now. Airline managers decide to use a lottery to determine which pilots will fill the available positions. Of the 8 captains chosen, 5 are female and 3 are male. Explain why the probability that 5 female pilots are chosen in a fair lottery is not the same as what I have written down here. I am missing the very important. 8 choosing 5. Okay, so the managers are sampling without replacements when they do the lottery. So there's a 40% chance that the first pilot selected for a captain position is female. Once that person is chosen, the probability that the next pilot selected will be female is no longer 40%. So the binomial formula assumes that the conditional probability of successes stays constant at 40% throughout the 8 trials of this chance. This calculation will be approximately correct, though, or the probability doesn't change too much as long as we don't sample more than 10% of the population. But in this case, we sampled 8 out of 25 samples, and that's almost 1/3 of the population. So we violate the 10% condition. So we can't use a binomial distribution there. Okay. So normal approximation for a binomial distribution. So as n gets larger, something interesting starts to happen to the shape of a binomial distribution. So if you take a look at this first graph here, n is equal to 10, same probability as this one where you have 20 trials, same as this one where you have 50 trials, all the same probability, same situation, okay? As the number of observations n becomes larger, the binomial distribution is going to start to get close to a normal distribution. This is a big concept. So the more the trials, the more normal the distribution. So you can see that we're starting to kind of head back towards that idea of normal distribution. So the more the sample, the more normal that it is. So when n is large, we can use normal probability calculations to approximate our binomial probabilities. So here are some ideas. So what we're looking for is how large is large. So that's going to be known as our large counts condition. So you're looking for when the number of trials times the probability is greater than or equal to 10, but also your successes also have to be greater than or equal to 10. So the number of trials times the probability of a fail has to also be greater than or equal to 10. And then in that situation, you can use a large count situation, which would allow you to use a normal approximation to calculate the probabilities of a binomial distribution or a binomial probability. So quick example of this. So sample surveys show that fewer people enjoy shopping than in the past. The survey asked a nationwide random sample of 2,500 adults if they agreed or disagreed that I like buying new clothes, but shopping is often frustrating and time-consuming. The population that the poll wants to draw conclusions about is all U.S. residents aged 18 and over. So suppose that exactly 60% of all adult U.S. residents would say agree if asked the same question. Let X equal the number in the sample who agree. So First thing that we're going to do is make sure that it is a binomial random variable. It meets all four criteria for bins. It is a binomial random variable. You could read it over. Next, we'll check the conditions for using a normal approximation. This would be, actually, I should go back to the I. So I is independent. So it isn't actually independent, but because the population of U.S. adults is greater than 25,000, so you're looking at it, your sample is definitely less than or equal to 10% of your population. It's assumed that the sampling without replacement condition is met, so you can consider this independent. So now let's check the conditions for using a normal approximation. So the number of trials times our probability of success was going to give us 1,500, definitely greater than or equal to 10. And the number of trials times the probability of a fail is going to give us 1,000, also greater than or equal to 10. So we can say that this is approximately normal. So if I'm looking to calculate the probability of 1,520 or more of the sample agrees, I can use a normal distribution. I first have to find my mean and my standard deviation, which we did in the previous video. So I'm just going to take the number of trials times my probability, gives me a mean of 1,500. The standard deviation is found by the following. It's going to give me 24.49. Both of those calculations, formulas rather, are located on your reference guide, so you do not have to memorize them. You could find a z-score and use that to find your probability. You could also just use your calculator with a sketch of where you're looking for. This would be norm CDF of 1520. Is your lower bound, not extreme upper bound. Your mean is what you found here at 1,500, and your standard deviation 24.49. Either way, it's going to give you a probability of 0.2061. So the probability that 1,520 or more of the sample will agree is about 20.6%. And that is it.